Hello and welcome to lecture 2 of the lecture series. Today we're going to be talking about electric voltage and ground. The contents are shown here, so we have the definition of voltage, a physical intuition behind what's going on, and practical notes for voltage and grounding, as well as a quiz at the end to test your understanding of what was discussed here. So let's dive right into it. So voltage is the energy required to move an elementary charge from one point to another. So you have a point A to B here, and if you use this polarity, this sign here, plus and minus given here, VAB is defined as the rate of change of work or energy spent for each Q of charge. So for example, so in this case, we have W, which is work, is the amount of energy you spend to move something or spend that energy to transfer the energy to some object, for example, in this case electricity. Work is measured in joules, and Q, as we've discussed before, is a charge and is measured in coulombs. If you have 1 volt, that is equal to 1 joule of energy per 1 coulomb of charge. So 1 volt is equivalent to spending 1 joule of energy for moving 1 coulomb of charge from one point to another. Now, if the electric field, which corresponds to the voltage across any given device, is pointed in this case from top to bottom in this fashion, the polarity would be plus minus, where the electric field emanates from the positive and goes to the minus sign. That's the convention for voltages. And as we discussed in the previous lecture, the convention for the current is to go from the positive to the negative. That is a conventional current, whereas the actual electrons flow from negative to positive. Now let's talk about the physical intuition behind what's going on here. So suppose you have a piece of copper, which is a metal, and in this case you have metallic bonding between the electrons, the free electrons, and the positive ions. Now, the way I like to think about metals is that they have seas of electrons. I've heard that before elsewhere. I can't remember who said it, but basically you have many trillions of free electrons that are readily able to move due to a random thermal motion. So motion due to the presence of a certain temperature that is greater than 0 Kelvin, which is an absolute unit of temperature. So as long as you're above 0 Kelvin, you're going to have some random thermal motion, and as you increase the temperature, you're going to give more and more thermal energy to the particles, and in this case electrons, and they're going to have even more crazy random thermal motion. Now the other mechanism to move electrons is to apply an electric field across the terminals of the device carrying those electrons. So in this case I have some positive ions, negative ions, which are electrons, and I've applied a voltage across the terminals, and the electric field, as we discussed before, is going to point from positive to negative, and the electrons are going to go the opposite direction of the electric field, so from the tip of the arrow to the end to the electric field, so from left to right in this case. Now, we talked about random thermal motion. We got wiped here at some point. Now, as the electrons move about in the wire, in the metal wire, and in the device, they're going to be, so as we said, moving randomly as a random thermal motion, and also moving with the electric field in a given direction. As they move, they're going to be colliding with the lattice of copper atoms. As they collide with the lattice, they're going to be releasing some of that energy that they've gained from the electric field and the random thermal motion, that temperature. They're going to be losing that energy to heat produced by that collision to the lattice. Now, if you had a light bulb, for example, you would have not only that heat lost to the lattice, but you would also have electrons exciting other electrons into higher energy levels, and then when the excited electrons go to those higher energy levels, they're going to be unstable, and they want to emit that energy as photons and jump back down to the lower energy level. And in that case, in that manner, that's how you have light bulbs operating. As you can tell, they heat up, and that heating up is due to the collision with the lattice, and the light comes from the emission of photons from that sort of quantum idea of jumping from one level to another, which we're not going to really discuss in this lecture series, as it doesn't relate for our purposes. Now, if you look at the random motion, don't get scared by this diagram here. It's just two different scenarios. So one scenario is when you have no electric field present, which is shown in yellow here. You have an electron here, and it's going to be moving about in a random motion, in a random manner. In this case, it's moving in this direction, up here, and then back down here, and then up here. And on average, you could say that due to only the thermal energy available, it's not really going to move. If you have a population of electrons and you randomly thermally excite them, the net motion is zero. On average, they're going to be staying in the same place. They're just going to be moving about and coming to the same place on average. But now if you apply an electric field from here to here, right to left, the electrons, as you recall, they move from the opposite end to this direction. They move against the vector field of the electric field. And what you have going here is that you have the net, you're going to create a net motion towards the electric field here. You're going to have still the random thermal energy, the random thermal motion, plus the motion caused by the presence of the electric field. And this creates what's called drift currents. These electrons are going to be drifting due to the presence of the electric field. And in this case, you can see that they move from here to here due to the presence of the electric field. So that concludes that idea of the thermal motion. So now let's go on to talking about some practical notes. So if we talk about, if you see this two-terminal device here as terminals A and B, we can see that the polarity is defined as plus being here, minus being here, and that is 3 volts. So what this is telling us is that as you go from A to B, you have a drop of 3 volts. You have a voltage drop across this element of 3 volts. The way I like to think about voltage drops is if you think about ground, actual physical ground, the earth, if you have a ball being held here by someone and it has a mass m, it has a certain height from the ground h, the potential energy for this ball at that particular height is m, which is the mass, times the gravitational constant of the earth, acceleration due to the gravitation of the earth, which is a constant near the earth, and you're going to have the height of the ball, and that's going to be h. You can see as I increase the mass or the height, I'm going to have a higher potential energy. And if I let that ball go, it's going to get released, and it's going to lose that energy to, or that energy is actually going to get converted to kinetic energy and also friction due to the air resistance. So similarly, you can think of that as the drop. So for example, 3 volts are going to be dropped across here, this device, and so 3 volts are being expended. They're being used up for a current to flow. In this case, these terminals are open, but in reality, you would have a closed circuit, and then a current would flow, and that would correspond to this. So 3 volts would exist across the terminals, and a current that is appropriate with that given voltage would flow through the device. Now, VAB is the same as the opposite of VBA. So if I have a drop from A to B, and the polarity is defined as this in this manner, if I flip the polarities now, I could say there's a rise of negative 3 volts as I go from A to B. This might be initially confusing, but you can also think about it as negation in the English language. So if I say I don't not walk, that is the same thing as canceling these two negatives. So -1 times -1 equals +1. That's sort of how I like to think about it. So I do actually, in fact, walk. That's one way to think about it if you like to think of negation in that manner or in terms of multiplication. So in this case, if I go from A to B, I have a drop of +3 volts, or if I go from A to B and the polarity is reversed, I would have a rise of -3 volts. And you could also prove it mathematically here in a trivial manner. So VAB equals 3 volts, I plug in 3 volts here. VBA equals -3 volts, -3 volts. So in this case, 3 volts equals negative times -3 volts, so that's 3 volts equals 3 volts. Now let's talk about electrical ground. So as we discussed, voltage is defined between 2 points. if I were to look at this generic circuit here, I would need to use my digital multimeter or some other device that I measure voltages with and go across each element and probe it and look at what voltage I would get. In reality though, this is called the floating voltage. This is called a floating device right now. It's, there's currents flowing here, but this device is just sitting on a plane by itself. There's no reference to any other locations or other voltages. In reality though, we'd like to be able to just use one point, one probe, and probe different places in the circuit, in a more complicated circuit, for example. Now what we do here is we use a symbol called ground, and we usually go to the negative side of the supply voltage, and we ground that terminal or that point in the circuit. Now in this given branch here, I could put the ground anywhere, as long as since the wire, there's no voltage drop across an ideal wire, the potential is the same. So you're gonna have a ground here, it would still be the same 0 volts reference point here, the ground. Now what this enables you to do is, okay, I put my negative side of the probe here, the negative probe here, and I go around anywhere I'd like, and I could measure with the positive side of the probe, I could measure the voltages there. Now give me the voltage on the screen, it would be some value. So that's one advantage that you would get there, and that's, I believe, the primary advantage. So in practice, we measure point voltages, as I discussed just now. Now, there's this idea of earth ground. So the earth, as you know, is an enormous body of material, rocks, metals at the core, and lava and iron and all sorts of things. So what happens is, if you perturb, so as you know, everything is made out of charges, plus and minus charges, and when you have a large body of positives and negatives, they cancel each other out, and you see a neutral body, and there's no net electric field present there, according to Gauss's law. Now, if you perturb the charge distribution of the Earth at a particular location, so around here, for example, if I have a voltage source there and I move around charges here, what's going to happen is that these charges are going to redistribute themselves in such a manner that you have a net 0 charge present. So this makes the Earth a very good ground. It makes it a 0 volt reference, because there's, at any given point, there's almost no net charge, because there's so many free electrons, seas of electrons flowing around and basically making it neutral. Now, if you look at the outlet at your house or at your business, you would see a 3-prong connection here, which is what it should really be for safety. You would have a neutral, a hot, and a ground connection there. And what this does, it allows you to avoid shock hazards by having a connection to the chassis of the electrical device you're working with. So in this case, you have a DC power supply and a signal generator. The DC power supply is going to supply a DC voltage, and SIGGEN is going to provide is going to provide a AC voltage. Now suppose you were to somehow use these together, you would need to bias an amplifier with the DC power supply, and you need to test the input with a small AC signal and see what the output is, for example. That's something you would do in a typical application. And what's going to happen here is that you're going to connect the 3-prong connections of neutral, hot, and ground for both of these devices to the wall outlet. Now ideally you would like it to be 0 resistance between the grounds for the 2 different devices. Otherwise, if there's a non-zero resistance there, you would have a voltage drop, a parasitic voltage drop across the wires that would connect the ground terminals of the devices, and that's not ideal. You don't want parasitic drops. You want the voltage that you produce at the output to go almost perfectly to the device you want to provide it to. Now for the shock hazard idea, the idea here is, I'll show you that in a minute. So let's first go through the different types of grounding. So if you have a common return or a floating return, you have just a voltage source, a load, you connect them, and you have some current flowing according to Ohm's law here. So you apply a voltage, there's a resistance there, and you get some current out of that. Now in the schematic, you would have a voltage source, the load, and you would have a return path shown in this manner, and this is a floating return path. in terms of how you would actually wire that up, you would have a supply plus minus terminals, the load, and you would connect the wires there accordingly. There's no worries of ground or anything. It's just a supply. It's a floating supply, a floating voltage there. Now, if you have a chassis return path, you would have this symbol here for a chassis. You would have the voltage source, the load, and basically what's going to happen here is you have the supply plus minus the load. You connect the plus to the load, and you have the minus go to the chassis, and the minus emanate from the chassis to the negative supply here. The third type is the earth return. So if you have if you want to basically not have a floating voltage, you want to have a common reference for multiple different circuits, you would need to ground. The negative terminal is usually what's used to ground. You could also ground it at the top, but that's going to give you ugly minus signs. You don't want to deal with that. So you just ground the lowest potential of your circuit, the negative side in this case of the source, and what that's going to give you is your supply, your load, the connection between them. This would be the neutral connection. This would be the hot. This would be the ground. Now, common misconception would be to say, okay, let me just connect the hot and the ground to my device. But in reality, let me connect my laptop to the charger. In reality, though, what needs to happen is you need to connect your floating supply as before. But then what you want to do is just add this symbol here. What you're doing here is you're making it so that the negative terminal here is sitting at 0 volts. So it would be common with other electrical devices. They would all have the same reference. And typically you have very low resistance wires connecting the ground connection to the prong that is ground to the breaker box and to the ground rod. And because of that, there's almost very, very small parasitic drop across the resistances there. Now, you might wonder, okay, well, if the resistance to ground is very small, if R is almost 0, and this load, let's say it's 100 ohms, for example, why wouldn't my current just bypass? If current does indeed take the path of resistance, why wouldn't it just go directly to the ground here and just bypass the load altogether? I'd like you to stop the video and just think about that for a second and try to see if you can answer that question. So, assuming that you've given that a try, I'm going to explain why that's not the case, why the current actually flows through the load here. So, basically, if the other scenario was true, if the current would bypass the load and go just through the ground, the issue with that would be that there's no common return path. So you would have the positive here, the negative here, but once it goes out here, if it could, there is no return path here. So therefore, what's going to happen here is, as before, you're going to have the floating connection here, the plus and minus here, current flowing here, but then this grounding here is going to just set the 0 volt reference to the negative terminal here. That's all that's going to do. There's no current actually flowing here unless there is a short or a hot wire coming loose inside the device, in which case instead of flowing through you, which you have higher resistance than the earth, the current's going to flow instead to the least resistance, which is the earth, and in that fashion it's going to protect you. Another application is for as you may know, ICs are very sensitive to electrostatic discharge. So it's a very common place to wear smocks at the workplace and to basically ground yourself at the feet and with your hands to a grounding mat on a table where you would be working. The reason for that is electrostatic discharge is thousands of volts, and it could easily destroy ICs, and you would never be able to detect. Sometimes you can detect. Sometimes you can see that a path is blown. You can see a trace is blown. But in a lot of cases, you may not be able to see any damage, and you would have a complicated circuit. You have no idea, okay, is this component failing? Is this component failing due to ESD? So companies, electronic companies, including mine, have a lot of precautions and a lot of processes to avoid electrostatic discharge. And so you have to follow those. So it's a very important problem. You have to make sure not to destroy thousands of very expensive equipment by protecting yourself and basically following the guidelines to avoid ESD. Now let's move on to another concept here, which is combining voltage sources. So that's another practical application there. So say you have a voltage source here with the positive and negative terminals defined as such. It is 3 volts, and the ground is here. You've grounded at the negative terminal as is common. So if you put the probes here for your multimeter, for example, you're going to read what? Plus 3 volts. Now that looks like a 2, that should be a 3 volts. Now if you look at here, you have 2 voltage sources combined of the same voltage. It's grounded at the negative terminal here. You have some terminals going out of here. Locally, if you were to measure between here and here, you would have 3 volt drop here and a 3 volt drop here. But if you were to, as you have grounded here, if you were to put the positive probe here of the multimeter and the negative probe here, what you would actually see now is 6 volts, because you're going to be adding these 2 voltages. You're going to rise 3 volts and rise again 3 volts, and you get 6 volts in total. Now here's an important example is when you have a dual supply, and this is useful for powering up the op amps or amplifiers. What this does is it allows you to have a plus VS rail and a minus VS rail, in which you can have a certain swing. Your signal can swing on there in between. So you would have 0 here, and you have some swing, positive and negative. And we're going to discuss that either later or in a different lecture series when we talk about amplifiers. So what you do is if you have equal voltage supply, is you would have the positive terminal at ground for one of them and the negative terminal at the other side, and you would measure negative 3 volts here, because you're going from 0 volts set here, you're dropping negative 3 volts, and you measure negative 3 volts. Now if you start from ground and you go up, you have a rise of 3 volts, and you measure 3 volts there, so plus 3 volts here and a minus 3 volts down there. Given that, now we should be ready to move on to the quiz. What I'd like you to do is find the voltages at the labeled nodes. Now note that I've said labeled nodes, and these are particular points. So that's a hint for you. Another hint for you is that I have a ground terminal here. So given that, I'd like you to go ahead and fill out this table here, showing the voltages at these various nodes. So I'd like you to stop the video and give it a try. So I'm assuming that you've given it a try, so I'm going to go ahead and solve the problem with you. So I'm going to start, since we're talking about node voltages, we know that voltage has to be measured between 2 different points. So if we're talking about node voltages, there has to be ground somewhere. So I'm going to go right into the ground here and start from there. So for example, if I go to the right here, I have 0 volts at ground. I rise 10 volts. So at F, I'm going to see what? 10 volts. Now keep in mind that when you're measuring this, you're measuring it with a high impedance probe coming from a digital multimeter or a scope. So you're not going to be drawing current there. You're just going to be measuring the voltage. So don't worry about voltage divider is going here, if you know what that is. So now you could say that it's open. So that's the point that I was making there. So now let's go on to measuring the voltage at G. So again, we're going to have start from 0 volts, go up 10 volts, go up another 10 volts. That's another 10 volt rise. You're going to have 10 plus 10, that's 20. You're going to have 20 volts of voltage there. Then at H, you have another rise, 10 volts, 10 volts, 10 volts, and you're going to get 30 volts. And again, keep in mind, this is H, this is 30 volts at H with respect to ground down here. That's a very important point to keep in mind for future lectures. Now for E, we're going to have 0 volts. This line is also 0 volts. You're going to drop down 10 volts, and that's going to give you negative 10 volts. That is negative 10 volts. At D, you have 0 volts down here. You rise 10 volts, and that gives you 10 volts up there. Now, this is still 0 volts, ground here, ground here. This whole branch is at 0 volts, 0 volts. So here, if you rise up 10 volts, you're going to be sitting at C, and that is at 10 volts. Now, if you go up here again and we go to B, I have 0 volts here as it's connected to ground. We're going to trace it through, and it's going to be 0 volts. I'm going to drop 10 volts, and if I drop 10 volts from 0, that's going to be negative 10 volts. Negative 10 volts. And if I'm again sitting at 0, and if I rise 10 volts, that's going to give me 10 volts. I think the video has been very long by now, and I hope you've gotten something out of it and you've enjoyed the video. I'll see you in the next video. Thank you.